Okay, so now we're going to start looking at what we call statically indeterminate conditions. So let's look at this beam here. And I'm looking at this, I have a beam that's grounded between two walls. If I draw a free body diagram of the beam, I'm going to have some reaction force at B. I'm going to have P pulling down. I'm going to have a reaction force at A. Now, it's fixed at both ends, and the force is applied in the middle. So if we write our equilibrium equation for this, we've got the sum of the forces in the y direction is going to equal to 0, and we're going to say that upward is going to be positive. And so what that's going to give us is RA plus RB minus P will have to be equal to 0. So P is going to be equal to the sum of RA plus RB. Now, can we solve for these reaction forces here? Because typically we're going to know what P is. And no, we can't, because I have one equation and two unknowns. This style of problems is what we call statically indeterminate, which means that we can't solve the problems using statics alone. And since I have one equation and two unknowns, the only way that I can calculate this out is I need a second equation. And then once I have the second equation, I will have two unknowns. And so what do? What can the second equation be? So what we're going to add to this is what we call a kinematic or compatibility equation. So kinematic, also a compatibility equation. And so basically what we're going to do here is we're going to look at this problem and go, do I know something else about this problem? And typically we're going to be looking at it in terms of displacement. So in this case, I know that between point A and point B, well, there can be no deflection between A and B. The deflection has to be 0 because it is wedged in between these two walls and it can't go anywhere. Now, that does not mean that section there, AC, can't get longer, but by whatever amount that AC gets longer, CB is going to have to get shorter. So what do? How do we take into account this compatibility equation? So now if I take a look at the free body diagram of this, so if I cut it here and I cut it here, I can take a look at the internal forces. And also, not only can I look at the internal forces, but where I'm cutting it, I'm completely removing P from the equation. So if I look at this upper guy here, that is just, all that's in there is the force in A. And I can figure out, okay, well, the deformation on that one's going to be the force in A, the length of AC, divided by the area over AE. So if I look at this guy here, I can sit there and go, oh, well, I've got the internal force there, and I can go, well, the deflection in that is going to be the force in B over the length of BC, because that's over which it acts, times AE. I know these have to be 0. So we're going to call this the deflection from AC, the deflection from BC. So I know the deflection from A to B is 0. And that's going to be whatever the deflection at AC is plus whatever the deflection at BC is. Now, naturally, it's going to turn out that one of these is going to have to be a negative force, a compressive force. And taking a look at it with the way that we drew it, FB is going to be that compressive force. So if I go and put these together, that means 0 is going to equal to FA over LAC divided by AE. Minus, because FB is compressive, it's going to be a negative force, FB LCB over AE. So now I have that second equation. Because now if I look in this, I have those reaction forces. Now I know in the last slide I used R for my reaction forces. I really should have used F. But if I pull that equation down, P is equal to FB plus FA. And once again, like I said, since we typically know P in the problem, if I look at this, I have FA, FB, FB, FA. I have two equations, two unknowns. You can solve it with any of your favorite simultaneous solving methods. Typically, just rewrite this as FB is equal to P minus FA, and then you go and you plug that back into your FB. But now what we've done is we've taken this thing that we cannot completely solve by statics, and we've put it together that we can solve it using a compatibility equation. Now this one here, we've got just our rod that's completely set in between two planes. So in this case, I know from here to here that there can be no overall deformation. But, especially in the examples that we're going to look at, we can start playing around with stuff like this and going, okay, well, I have some gap there. And if I apply a load here, well, I know that it's going to be able to deform up to, I know it's going to be able to deform up to what that gap is. And so basically the whole thing with the compatibility equations is figuring out, okay, where can we look at things and go, okay, there can be no deformation here. Or there can only be this much deformation here, and that's what's going to drive the entire problem. Okay, and so this is how we go about solving a statically indeterminate problem using kinematic equations.